Part 3. Using reasoning to find a counterexample to a conjecture. What is a counterexample? Well, it's an example that doesn't, the conjecture doesn't cover. An example that argues the conjecture. Okay, so let's get some idea of what that looks like in the following examples. Find a counterexample for each of the following situations. So the statement of the conjecture is, if you live in a country bordering the United States, then you live in Canada. Well, here's an example of something that would be a counterexample. How about Mexico? Okay. If a quadrilateral, a four-sided shape, has 4 right angles, then it is a square. Well, I know that rectangles are four-sided, and I know they all have right angles, but they are not a square. C. Odd whole numbers less than 10 are prime. Well, our odd whole numbers are 1, 3, 5, 7, and 9, of which 1 and 9 are not considered to be prime. 1 does not have a category because it's not prime or composite, and 9 is composite. All birds can fly. Well, except an ostrich. Okay? And E. All cats are born with a tail. Well, there's a cat named Manx that has no tail. So, that conjecture is also disproved by the counterexample. More support for a conjecture developed through inductive reasoning will strengthen the conjecture but does not prove it. Even if a counterexample is not found, it doesn't mean the conjecture is true. It is not possible to try all of the possible cases, so it is not possible to prove a conjecture. On the other hand, one counterexample is all it takes to disprove a conjecture. Once a counterexample has been found, the conjecture is invalid or useless. If it is easy to find a counterexample to a conjecture, the conjecture is very weak. To strengthen it, it's important to test the conjecture to find counterexamples. Sometimes a conjecture is made that seems obvious, but once you do a little testing, you quickly find a counterexample to disprove it. In this case, you may ask yourself, was I completely wrong? Is there any truth to my original conjecture? Okay, let's go through the following examples. Number 1. The sum of 2 prime numbers is an even number. So, 2 examples where the conjecture is true. Okay, so prime number could be like 5 and 7. Okay, so those are both prime, and that would give me 12, in which case, yes, that is a true thing. Let's go with another prime number, 11 and 23, and that would make 34, which is also an even number. But we have one counterexample, and that would be 2, which is prime, plus any other prime number. So 2 plus 3 equals 5. 5 is odd, therefore our conjecture is disproved. Matt found an interesting numeric pattern in question number 2. So we took 1 times by 8, add 1, we get 9. Okay, and then we take 1, 2, or 12 times by 8 and add 2. Okay, so you can see we just keep adding digits on, timesing by 8, and then adding the number that represents how many digits we have. And if you'll notice, it starts 9, 9, 8, 9, 8, 7, 9, 8, 7, 6. So it looks like we're going down by 1. Let's keep going and seeing if we can find a counterexample. So we got 1, 2, 3, 4, 5 times 8 plus 5. Go ahead and calculate that out. 1, 2, 3, 4, 5, 6 times 8 plus 6. 1, 2, 3, 4, 5, 6, 7 times 8 plus 7. 1, 2, 3, 4, 5, 6, 7, 8 times 8 plus 8. That's a lot of 8s. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 8 plus 9. Okay, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 8 plus 10. Okay, so when you multiply that out and then add, because remember multiplication happens before addition, this one gave you 98765 and 98765 and again you can pause the video to verify all of this. 9876543, 9876542. So far his conjecture seems to look good. 987654321. Okay, and what about the last one? Okay, I am getting 9876543, and then I get a 1290 when I do this calculation. And that, my friends, is where Matt's pattern falls apart. So the counterexample would be at the 10 level. Example 3. Give two examples that support each conjecture and then one counterexample that shows it's false. The sum of two perfect squares is an even number, part A. So the sum of two perfect squares. So we could take 9 and 49. Okay, those are both perfect squares. The sum means to add them, so that would give me 58. Or we could take 4 and 16, and we would get 20. But what happens if we were to take 25 and 36? Again, both perfect squares. When we add them, we get 61. So the first two supported. We get even numbers, 58 and 20. But my last one is a counterexample because I get an odd number when I add those two perfect squares. Okay, part B. The square root of a number is smaller than the number. Okay, so let's go square root of 81. We get 9. 9 is definitely smaller than 81. What about the square root of, let's go 144. Okay, that of course is 12, so still smaller than 144. So those are my examples that prove my conjecture or help to prove it, okay, because you can't actually prove it. But if I were to go square root of 0.25, square root of 0.25 is 0.5. Well, if I had 50 cents compared to 25 cents, my answer here is actually larger than the original radicand. So therefore, I have a counterexample that shows my conjecture to be false. So key ideas. A conjecture is invalid when you find a counterexample to a conjecture. A counterexample may be used to help you revise a conjecture. So in part B, for example, we could revise it and say the square root of a number greater than or equal to 1. Greater than 1, I guess. Because actually if you square root 1, you get 1, which is not smaller. Okay? So greater than 1. Okay? So that would be your revision. If you said that, then your conjecture would be a little more difficult to disprove. Okay, great. Give these a try, page 22, 1, 2, 5, 16, and 17, and show your teacher when you're done.